I don't know. Graph is graph. So it's very similar.
At first I did.
If I were to do it in Arabic, for example, equation would be معادلة and x.
Stadium where you can go.
So it's here. Did you send it to like whoever wanted to study philosophy for Arabic?
I don't know.
Because there is no scientific word. History, philosophy. These are not.
These are really easy.
I studied
Nikos.
Which is really. Is it common or is it?
It's common. It's common. If you study, but if you study I doubt that.
My friend is also. It's good.
شوف في الأول ويندوز ندير لانترو ما نطولش ساعات غير صورني مزيان بغيت نحطك سوبرفيزي تتوك على هذا الموضوع نو نيد فور داك الشيء ديال مسح شحال من حاجه يو ماي اسك ريلاكس كلنا عارفين اش كامل فهمتي تست عطاتك شي سبب؟
No, where he learns machine learning because he is every time with me. Like to the classes and I don't know when he learned.
Do you cross the door?
We can do. So. This will come on, then you can push this, change colors, this, and then you use some kind of black.
Stop worrying.
So, hello everyone. Hope you're all doing well and hope you're happy to attend today's event. So before starting, talking about today's topic, correlation theory, I'd like to first give you an introduction about what's even the math society. A lot of people here came today. A lot of people is even their first event today in math society. So here we believe in three words: think, calculate, create. Why? Because when you have a problem, we first think abstractly, then we calculate to make our ideas precise, and finally we create stuff that were never created before. And how do we teach you that? Well, we've done multiple events before. Last semester, we were able to do the math behind AI, machine learning neural networks, poker and game theory with Professor Kevan, and Interstellar. Moreover, this semester, we were able to do the math behind cryptography and cybersecurity, and the math behind case theory with Professor Ivan. Not only that, we also have our famous series, the undergraduate seminar, where we have, for example, our subjects about door and irrigation optimization, or string theory, but also the undergrad seminar 4, where we had about dark energy and extension of the universe, Bedford's law, and Dutch-Kuta methods in differential equations for neural networks. Pretty much all of you all know that, so let's talk about the important thing, the upcoming events, right? So, we have 3 events left and 3 big events. First one is the 25th of March, the Math Behind Finance with IBCM as a collaboration. Whether you're interested in making money with no risk, and how does that work, and why would that be true? Then note this on your calendars. Then, next one, we would have the Didathon, which would be the 17th of April. If you're interested in doing your first competition to research and tackle a real-world problem, then that's the opportunity for you. And finally, the undergraduate seminar 5, which would be the only undergraduate seminar of this semester. And why am I mentioning that now? Because you would see it's 23rd of April, so it's pretty far. Because the deadline to apply for the undergraduate seminar would be the next Tuesday. Again, for the people who doesn't know, so the undergraduate seminar is basically an opportunity that we give to students where they apply, and through their application process, they get accepted to conduct a 2 weeks research project with us, the course of the Math Society, and finally get reviewed by one of our professors, Professor Petrat, Professor Kevan, or Professor Ivan. So if you're interested in doing your first research project and having your first research experience with us, and you have a subject in mind, or you don't, then don't hesitate to apply. So be ready, because in a few minutes, we'll start the actual talk. Thank you very much.
Okay. Hello, everyone. Before I give a little introduction about myself and Yossi, who we're going to present causal machine learning, let's talk about what actually is causal machine learning or machine learning in general. Does anyone know what machine learning is?
Learn new the machine?
Yeah. Yeah, so it's a subset of artificial intelligence that allows machines to learn through patterns and behaviors that we teach them, right? So there are two different kinds of machine learning. We have traditional machine learning and we have causal machine learning. And today we're going to learn about the difference between those two and how one can be deeper than the other and where they differ, okay? So we're going to start with a little bit of an introduction so you guys don't just come for the talk, you also come to meet us, right?
Okay, so most of you know, my name is Yosias. I'm originally from Ethiopia, and I'm a second year IAM student, and today I will be talking about causal machine learning. I will be taking you throughout the whole presentation with...
Hello, my name is Idamis Andujar. I'm from the Dominican Republic. I'm a first-year industrial engineering major. I'm 18 years old, and today we'll be talking about the differences between causation, correlation, causal, and traditional machine learning.
Okay, so hope you guys are excited. So for today's plan, so just so you know, like it doesn't matter if you don't have any background on this about probability, maybe causation and correlation, machine learning, that's fine. We're going to start from the very simple one. We're going to explain everything. And for your understanding, we're just going to be using one example. And this example is going to be, we're going to act as an e-commerce company. And then we're trying to figure out what is the probability of like us retaining a customer based on our delivery time. So by playing with the delivery time, how can we affect the customer retention probability? So for our today plan, first of all, I'll start with probability and random variables, and then Idamis will explain about causation, correlation. I'll continue with DAX and disapparition, and then she will follow up with interventions, and then we'll finish up with identifiability, and then at the end we'll have a question and answer session, and then after that we'll do a Kahoot. So pay attention, because yeah, there will be Kahoot questions. So let's start with probability and random variables.
If you'll let us.
Okay, wait. Okay, probability and probability foundation and random variables. So why do we need probability? Like, of course, because we don't know what's going to happen in the future. We can never be certain. Like, for example, we don't know how many demand we're going to get in the future. So we can say like there's a chance of happening. So here, like probability allows us to describe this uncertainty mathematically. So instead of saying okay, there is a chance, we need to describe it like in numbers. Yeah, that's where it comes random variables. Random variables basically change the qualitative into numerical values, and for example, we can say, okay, if we throw a fair coin, what like we can say, okay, we get heads or tails, but we need this in numbers, so we can change it to 1 or 0. That's how a random variable works. There's two types of random variables. The first one is discrete random variables. This is for countable things, integers. So here, for our main example, customer retention, the customer stays, we can assign it an 1, and then if the customer leaves, we can assign it 0. Another would be the amount of customers that stayed. This is, we cannot have like 1.5 customers stayed. We can only have like 1, 2, 3. This is countable. So that's why we use discrete random variables. The second one is continuous random variables. These are for things we measure. So, for example, delivery time could be weight, height. So these are measurable things. So delivery time could be 1 day and 10 hours. So the difference between discrete and continuous is discrete is countable, and then continuous random variable is something we measure. So now you know this, we can move on to joint and conditional probability. So joint probability is the probability of two variables happening at the same time. So, for example, here we have the customer stays or leaves. Even though we said like for delivery time, you can have 2-3 days. In this case, we will assign it 1 for fast delivery and 0 for slow delivery to make it simplified. So here now we have, okay, for fast delivery, there's a chance of 0.5, which means 50% of our customers, they get fast delivery, and then the other 50% get slow delivery. And then out of those, 60% of them, they stay with us, and then the other 40% leave. So when we say joint probability, we bring those together. So like how many of them got fast delivery and also stayed with us. So that's where we can see 0.4. So that got fast delivery and also stayed. So here the middle 4 numbers describes joint probability. Joint probability is very important because it gives us all the statistical information that we need to describe variables. So now you know joint probability, we can move on conditional probability. Conditional probability, most of you guys know this, it is trying to know the value of a variable given that we already know the value of the other one. So we're using the same example. Here we can take, okay, so here it is the same numbers, but we're going to calculate the conditional probability together. So now we're going to decide, okay, we can take, we know if it is fast delivery, what is the probability of the customer stay? So basically for joint probability, we have a sample space of 1. Now we change this, since we already know it is fast delivery, we change it from 1 to 0.5. So this will be our sample space. So the conditional probability will be 0.4 divided by 0.5. So it will be 80%, given that it's a fast delivery. This is a conditional probability. Okay, so now we can discuss about independence. Dependence, as you know, mathematically it is like if we can change the value of a variable by affecting the other one, is it one of the variables is it dependent on the other one? Mathematically, we can calculate using this formula. So we can say the probability of x times the probability of y is it equals to the joint probability of x and y. If it is equal, then it is independent. If it is not equal, it is dependent. So using the same example again, okay, is fast delivery and the customer staying or leaving, is it dependent or independent? Now we can see, so what did we say? The probability of x, which is here 0.5, if we take x is equals to 1, and then the probability of y being 1, 0.6. So 0.6 times 0.5, is it equal to our joint probability? No, because 0.6 times 0.5 will be 0.3. And it is not equals to 0.4, which means it is dependent. So if we change the delivery time, then it will affect if the customer stays or leaves. So now we can talk about expectation of binary variables. So when we say we expected something, like if I ask you, why did you expect that we will get, okay, this amount of demand in the next month? What do you say? You say, oh yeah, I calculated based on our previous information that we have, I calculated the average. So expectation in simple terms is the average. So here, let's take delivery time. So on the first day, if we got like getting a delivery time, we always order, and then the chance of you getting your Amazon package in 1 day is let's say is 0.3, the chance of you getting it in 2 days is 0.5, and the chance of you getting it in 3 days is 0.2. So your expectation will be the average of this. The way to calculate it will be 1 times 0.3 plus 2 times 0.5 plus 3 times 0.2. So this will be around 1.9 around 2 days. So that will be your expectation. But it is different when it is binary. Binary variables, as I showed you, like as I said earlier, was 1 or 0, so the customer stays or leaves. When it is binary, we cannot calculate the average, but rather it would be the probability of the customer staying. So out of 100 customers, if 60 of them stayed, it will be 0.6 will be our expectation. So for this expectation now, if we do it conditional, it will be, so the basically instead of probability of y will be the probability of y given that x. But this doesn't tell us like if it is causing it. It just tells us there's an association between those two variables. So Idamis will tell us about causation and correlation.
So sometimes variables are associated and sometimes they're not. And we need to know how to figure out when they are and when they're not, because we can easily wrongly associate variables with one another. So this is why we need to take a look at causation versus correlation. So has anyone heard these terms before?
Yes.
Yes. Okay, what have you heard about those?
We have class about
Okay. What is causation, do you know?
causation is when something happens and another thing happened after it and it's connecting
Yeah.
each other.
Exactly. It means one variable directly affects the other. And correlation, does anyone else know? Yeah.
It's us wrongly associating a thing affecting another thing just because they happen.
Yeah, just because two things happen at the same time, but they're not really causing one another, right? So sometimes, and I know this is going to sound a little bit complicated, but sometimes we can have a correlation and a causation because something that moves together at the same time can be caused by the other thing, right? But we can also have correlation without causation. So some things can move at the same time, but they don't have to be actually related. So how do we know, and where can we look so that when we are analyzing statistics, we don't get confused and don't relate things on our papers to something that they're not related, right? Okay. Oh. Okay, here we have an example. So if we just look at these two, without looking at anything else on the top, what do we see here? My computer shuts down and my video player won't work. I think these two are correlated because they happen at the same time, and so maybe my video player won't work because my computer is shut down. But not really, because just because these two happen at the same time doesn't mean they're caused by each other. If we actually take a look at the causes of both these incidents, then we can tell that it's because our computer ran out of battery. So this is basically kind of a simple way to put causation and correlation in contrast. Just because these two happen at the same time doesn't mean that they don't have a real cause and doesn't mean that they're related between each other, but they may have something that causes them that did two different outcomes, okay? So do you guys remember the example that we gave at the start? What we told you we're going to talk about throughout this whole presentation?
Cause the machinery.
Yeah, but we said that we were going to give a very general example, and that is about time, delivery time, and customer retention rates. Do you guys remember that? Okay. So before I jump into that, I'm going to give you an example of how we do that, but I'm also going to give you a little chart so we can see how we measure these types of relations. So we have a Pearson correlation coefficient, which is basically a formula that allows us to compare two variables and tell us if they're actually related to one another, right? And if these numbers turn out some type of way, it tells us about the relationship between these two variables. We have the Pearson correlation coefficient, and if it gives you between 0 and 1, it's a positive correlation, which means these two variables are moving at the same time in a positive way with each other, right? So they're moving together. If we have 0, they have no correlation, they have nothing to do with one another, And if we have a value between 1 and -0, it means they are correlated, but they're correlated in negative ways. And what this means is that when one goes up, the other goes down. Okay. How do we calculate this? What am I talking about? So the way we calculate this is by a very long formula that I'm just going to take the time to explain to you guys so that you know where I'm coming from, but I'm not really expecting you guys to apply this all the time, right? This is just simple Excel. You can move it around. You have the N always means the number of items and things that you have, like variables. And X and Y is, well, those respective coordinates. So you would do this formula and it would always give you one of these numbers, and then you would figure out here. So let's go back to that example. Let's talk about on-time delivery versus customer satisfaction rate and therefore customer retention rate. So we found an article that actually compared these two variables, and if we take a graph out of that article, we can see this. What can you guys see in this graph?
Negative correlation?
It has a negative correlation, yes. But does that mean that these are actually causations? Like one of them causes the other? Can we know that simply from this graph? No, right? But it's an easy way to kind of get confused, because if we just see this information, then maybe we won't know if these actually cause one another. And it doesn't really help our case on how to figure out if on-time delivery actually affects customer satisfaction. But I am going to give you a little bit of a spoiler. When we have different types of machine learnings, the traditional machine learning only is looking at this, right? So it's only looking at how these variables work, and it's learning that pattern, and then it's acting on this pattern. But it's not acting on what is actually causing it, and is not analyzing the actual graph that now Yossi is going to present to us. Okay.
So far we talked about, like earlier when I finished, I said, I talked about associations, but association is not enough for us. We need to know like what's causing what. So like they are associated doesn't mean, as she said, one is causing the other one. So how can directed cyclic graph can help us? So this one is basically, it turns the variables into nodes, and with an arrow, it will show us what's causing what. So here we can see that there's X causing Y, but also there's a third factor, customer income, affecting both of them. So there are two rules when we are doing, when we are using DAC. So as you can see, it says it's directed. That means that we should have, like, from one node to another node, we should have an arrow. And this arrow can only be in one direction, like this. So we cannot have a connection between Z and X just like this, but we need an arrow. The other one is cyclic. That means we cannot have a cycle between these variables. So we cannot have an arrow that is shaped like this, or we cannot have from Z to X to Y, and then going this way. Because we can start from X, go to Y, go to Z, and then come back to X. This will make a cyclic. We don't now want it to be cyclic. It should be a cyclic, so we cannot have this. So now you know this, we can move to deseparation. Before we move to deseparation, there are two things I want you to know. So the first one is confounding. So this one is basically when we mix a third variable, and then it is it makes a mapping effect between two variables, and we don't know what is actually causing what. So outside like our main example, let me give you another simple example. So one time, like you own a cat, and one time you go home, you see your lamp on the ground. So, okay, the cat is in the house, so the lamp is on the ground. So you don't know if the cat caused that, but you want to be sure. So you said, okay, let me test this. So you say, like, for the next 100 days, I'm gonna see, like, when the cat is in the house, if the lamp is on the ground, or if it's not on the table, it's not falling. So for the next 100 days, you do this test, and then out of those 100 days, only 10 of those days the cat went aside, but and it's only on those 10 days that you see the lamp on the ground. So what's like a normal person would say?
The cat caused the...
Yeah, the cat caused the lamp to fall on the ground. But what if, like this 10 days, there was an earthquake? So actually the earthquake make the cat go inside the house, and the cat is not actually the one dropping the lamp, but the earthquake is shaking up the place and the lamp went on the ground. So this earthquake would be the third factor. So for this, we need to condition on that, and we need to do a separate test where we force the cat to go inside the house when there's no earthquake, to test if the cat is actually causing the lamp to fall on the ground or if it is the earthquake. The other one you should know is collider. Collider is when there is two arrows pointing toward one variable. So in this case, it would be y, which is affected by the customer income and also by the delivery time. Okay, now you know this, we can go to deseparation. So earlier I showed you independence using a mathematical, so the joint probability, if it is equals to probability of y times the probability of x, then those two variables are independent. But deseparation tells us using the directed acyclic graph. So for this, there are three rules that we use. These three rules actually tells us not if they are deseparated, but they tells us if they are deconnected. So the first one is if there is a path between two variables and there is no collider on that path, the variables are deconnected. So as long as there is no collider in between them, they are deconnected. So here, which one is, if you guys remember, which one is a collider? I just showed you. T. Yes, right. So because we have two arrows pointing toward T, T would be a collider. So X and R, there's no collider between them, so they are connected. U till Y, it is connected because V, it is not a collider, rather it's a co-founder. So is X and U connected? No. Yeah, because we have the collider. The second rule, it is if there exists a path between X and Y and we don't condition one of the variables, then X and Y remain connected. So if we have any path, and then if we actually want to block that path, we can condition. So the green one here represents that we are conditioning on that variable. So in this case, it would be R and V that are conditioned. So easily, okay, from this, which of two are actually deconnected or not deseparated?
VT.
T to U, because V and R is conditioned, so they block the path. So it's here and here, they will remain connected, but if it is in between, these two will not be connected. So here T and U are connected, but anything that goes from this, from here to here, they will be deseparated. And then our third rule says that if we condition on the colliders or their children, they will no longer act as a collider. So we have T as a collider here, but if we condition on it, then it will not block our path. So they will no longer seen as colliders. So here another also says if we also condition on the children, here children would be, for example, here we did not condition on T, but if we have another connection here that is, let's say, B, and then if we condition B, we'll still make T not act as collider.
What do you mean condition?
Condition means, okay, for example, we can take our main example. There's a high and low income. So if we just take just the high incomes, and then if we separate them from the low incomes. So if we don't condition on this, you will merge them, and then you wouldn't know actually if it is because of the income that's causing the customer to stay, or if it is the actual delivery time. So basically you separate this two. Is that clear? Okay, so now we know this separation. Is can tell you about interventions.
Let's talk a little bit about interventions. So I'm just going to ask you a question. If we observe a variable, and let's say that variable is a phone breaking, if we observe that and just it fell on the floor, I'm just observing because it fell on the floor and it broke. Is that the same as me throwing the phone on the floor and letting it break? Are they the same thing? No, right? So we're going to talk about interventions, and basically that's what that is, because now we're asking different questions. Now we're not just observing in a natural state a variable. We're looking at that variable and we're saying, okay, but what would happen if I made it do this? Or if I force it to be something else? Or what would happen if I had not done this thing? So in causal interference, we're going to talk about interventions to evaluate the what-if questions, right? And to do that, we're going to have to use structural causal models, and we're going to abbreviate them into SCM. And so what these do is allow us to say, okay, but what if, right? So the goal of these is to model the data process so that we can see different outcomes when we make the variables do something else. Yeah, we're not just gonna see how they relate, but we're gonna see the different possibilities, as I just said. Here we have two different types of variables. We have the good ones, which are the endogenous variables, and these are the ones that you can very explicitly write down, like a phone breaking or anything, a delivery time, things that you can actually see and interpret. But then you have the bad ones, which are ones that we can't really interpret, and they are the exogenous variables, and they are the noise. So what do we mean when we say noise? Like, what? So noise just means things that we cannot tangibly measure or we cannot control. And this could be, for example, the phone broke, but what was the mood? What was the mood of the person? What was the day of the person? Things that we cannot control around us that may be interfering with our results. We always have to take into account the noise, we always have to take into account the noise when we're trying to analyze probability, because when we're doing causal machine learning specifically, it tries to figure out the source of things, right? As I told you, and it uses DAGs, right? Yep. It uses DAGs to find out the sources of those things, but to every node, there is noise. So, has anyone done coding? Yes, okay. In coding, when you're going to write something down, you have to write, do something similar to what we do with do operators. So when we're going to do an intervention, we need to do a do operator, which is basically like the code for the intervention. So how we write this down is, like this. We have to make the variable do something, right? So. And what this means is, yeah, I'm learning, guys. What this means is we are forcing X to become something else, which is this over here, okay? We are no longer observing the variable in its natural state. We are now forcing it to be something else, and that's what we do with do operator. We have to condition this variable so that we see it in another lens and we can answer the questions that I just told you about. What if we force it to do this, or what if we had not done the other thing, right? I have to release this now. Yay. Okay, so we have 3 steps for SCM. And those steps include a graphic description. So the first one is abduction, and it's when we observe in the natural state our variable. So it's the first step, it's what we all do. It's kind of like the scientific process, you know, you have to observe the variable. And then you have the action, which is intervention or the do operator, which I just taught you about. And then we have the prediction. So when you observe the variable, when you force it to do something else, and when you predict it to do the future, then you can teach a machine to do the same. Okay, now we're going to talk about identifiability and backdoor.
Just a quick question. Since we're relating stuff to that, I'm wondering, who creates the data? Or is it like an observation of correlations?
No, so when you're talking specifically in machine learning, the person teaching the machine, I guess, would have to create the DAG so it can learn from it and then predict up based on those like informations.
And based on what did the person identify the DAG? Is it like just their knowledge or
Investigation.
patterns they've seen?
Yeah, the different like points that we're talking about. So they first take into account probability, and then they compare the two variables and see where they're coming from, and then they would create the DAG.
Based on causation correlation, I see. I don't understand.
So
Wait.
yeah, go ahead.
DAGs are like assumptions we make. We can never be 100% sure because when you are creating DAG, you see, okay, there is a confounder that affects, that causes this, and this variable causes this. But you can never be sure like all the variables that are like taking into factor to cause something. So whenever you create a DAG, you just make an assumption that like this is all the factors that we're gonna take. These are the confounder, collider, and the variable that causes this. And then based on that, you can follow the rules. But you can never be like 100% precise on like creating the DAG.
Okay. And does like every step after that fully rely on DAG, or like it just takes it into account while measuring the causation?
Yeah, you continue by the assumption that this is like the complete DAG, that this is correct. Okay, so now let's move on to identifiability and backdoors. So basically when we say identifiability, basically what we're saying is can we calculate the cause effect using the data that we have? So can we calculate the effect of delivery time on customer retention? So here, as you can see, like we have the DAG here, but to be able to do this, like we want to block other factors. So here, the other factor would be the backdoor, so which is the customer income. So earlier I talked about disapparition. So based on that, how do you guys think we can block this backdoor pass? He just asked me a question about it's like the second disapparition rule. Yeah.
The condition on X.
Yeah. Not on X to condition on Z. So because the second rule says like if we condition any variable, the paths between them will be blocked. So once we condition on Z, then this path will be blocked. So we only see the effect of X on Y. So when we do that, it will give us this formula. So probability of Y given that X, this is association, not causation, it will turn to P probability of Y given that we force X, do X, what she said. So like we're forcing the delivery time. And then this to calculate it, we can have the equation of this. This might be a little bit overwhelming, but don't worry about it. I'm going to explain it, take it into pieces. So when we do that, here we have the broader version. So like the first sign, everyone knows it is the summation sign. And then the middle part tells us the probability of Y, which is the retention probability given that the delivery time in a specific income group. So we decide on the like X, which we said like do X, and then for the specific income group, and then we multiply that the probability of the income group being high or low. So we can do like a simple example real quick. So here we have, we want to calculate the effect of a one-day delivery. So we're forcing X to be 1 on a customer retention. So we're gonna check the value when Y is equals to 1. Customers belongs to 2 income groups, low and high. The chance of getting a a low income group is 0.4 and the chance of getting a high income group is 0.6. Also, observed retention rates are for low income group it is 0.7, so 70% of our low income group, they keep buying from our company, and the other like 90% of the high income group, they keep buying from us. So the other, for low income, the other 30%, they stop buying from us. The 10% high income group, they stop buying from us. So when we calculate this based on the formula up there, so we have what is the retention probability. Okay, we have the high income group retention, which is 0.9. 0.9 times will be the probability of the high income group, which is 60% of our total customers, they are high income group, so we multiply that by 0.6, and then we do the summation plus, and then we multiply the retention of the low income group, which is 0.7, times by the probability of the low income group. And then here we get, I think, one of it,
82.
0.8, yeah?
82.
Yeah. And then so if we take, in general, if we randomly pick any customer, there is a 0.82 or like 82% chance of the customer staying and keep buying from us. So now, what does this have to do with everything?
So what does this have to do with everything on machine learning, traditional, causal machine learning? Can anyone tell me a little bit? Because we've kind of hinted it through the presentation.
So instead of relying on the very obvious events that sort of happen in the same time, or that happens in the opposite order, you're relying more on the cause that is the cause for these variables. So it gives a better understanding of why something happens rather than just observing them.
Yep. And how could we use this information? Like, how is this knowledge useful for the machines? Why is it better to have a more in-depth knowledge of what is going on? Does anyone know?
Just like the mutations, let's say borderlines, guardrails.
Sorry?
To have the machine set guardrails on what is like the causation and how it should measure, rather than what's correlation.
For how it's gonna act, right? Like what it's gonna do. So yeah, exactly this. So the machine should learn the background or the in-depth way that we're working so that it can then react or do the actions that it should do and not just taking into account the superficial information. So just to give a little bit of a summary and how this relates to traditional versus causal machine learning. We've been talking about probability and we are specifically talking about causation and correlation between it. And traditional machine learning really just looks at how the variables move together and how they go up or down and what kind of relationship they have with each other. And they don't really take into account if it's one is causing the other. And so it can't really act on the cause, but just on the result of whatever is going on. And while causal machine learning really does take that into account. So what is the cause of this event or this variable happening? And traditional machine learning does not take into account DAGs. So it does not use digital acrylic graphs to see the sources or where we're going in our variables, while causal machine learning does, and that's why it can get a really, really in-depth knowledge about a situation. And deseparation as well. Then we're gonna talk about interventions. So traditional machine learning does not use any of interventions, while causal machine learning really asks the what ifs. And the same with identifiability. It tries to see what would happen if one variable does not happen or it does, and then it answers the questions based on how that affects the other variable. So yeah.
So now it's your turn to ask questions. So any questions? Anything?
No, nothing.
No? Nothing? Okay.
Wait,
Then we,
wait.
we'll just give you time.
Yeah.
How can I use it in the middle?
Okay, that's a good question. Okay, sure. So basically, if you take all of these factors into account and create a very complete digital equivalent graph, you could teach any type of machine to do any type of process with the knowledge that you would basically already have, right? So if, for example, we're talking about delivery time and customer retention rate, if we want a machine to tell us when we should deliver, how we should deliver, it already has all the information that can help us retain the customers, you know?
What should I prefer, this or AI?
It is a subset of AI.
Yeah.
How do you teach the machine that information?
We didn't do a research on that.
I'm guessing like coding, like you would code it.
Yeah, but I think you have to give like the dog to the machine. So it's like you have to give all the other factors, so it knows, okay, what's the, like, which backdoor should block. So if you give the machine, okay, from delivery time, how does it affect our customer retention? But if you also give it that, okay, we have a third factor income group, you need to separate it based on this to get the effect, then I would assume that, but I didn't do any research.
Yeah.
What were the three factors affecting the graph?
Three factors affecting the graph.
Or the rules of decomposition.
The rules of disapparition, you mean?
Yeah.
Okay, the first one is if there's a collider between them. So it's like a collider will block the path. The second one is if we condition. So if we condition one of the variables, it would be independent, it would be blocked. And then the third one is if we condition all the collider, and then like the collider won't act as a collider anymore, so the paths will be open again. Questions?
What field of work is it used?
Yeah,
Use it
the-
in anything, logistics, like machine learning, AI.
Yeah, everything.
Everything.
I mean, because you can teach it any kind of information. We specifically did it more in a logistics type of way because that's both our majors.
I am students.
Yes. But you guys can use it for any type. I mean, what is your major?
I am.
Oh, okay, well, someone else.
Logistics.
Yes.
I have a staff and we're working on causal AI, and you can basically apply it almost to any industry as long as there is data
Yeah.
that can be fed to the machine. And yeah, as you said, feedback. Even you can use LLMs to translate it to semantics to also feed it into the machine as well. So it can basically be applied to
As long as there's data.
finance, medicine.
It's anything basically. I mean, AI is the.
Can you please tell me the main difference between the traditional and causal machine learning?
Okay, so in general, you would have that the traditional is more as an overview, if you would have it. It doesn't really take a look at where the things are coming from. It just takes a look at how the variables are related and therefore acts on that relation, while causal really takes a look at the background and where it's coming from and therefore acts from its source, not really from the result.
Can you give a different example than the delivery time, please?
We can basically the cat in the lamp example that I gave you. That's basically like casual machine learning is like when you are forcing something, machine learning is observing. So for casual, you are intervening. You are actually forcing the, for example here, out of those 10 days, as if you remember the example, out of those 10 days, the cat went aside, we found the lamp on the ground. But those 10 days, an earthquake happened, so we do not know if the earthquake caused it or the cat. So what you do is you force the cat to go in the house, and then you will see if like the lamp is on the ground or not. So it's basically like do X means like forcing the variable to do something.
Specifically, if you do an intervention, it's not really like, oh, I'm gonna force you to do it so that I have the result. No, it's like, I'm gonna force you to do it to see what the result is so I can see what effect this specific thing has on that variable.
So we force the cause, like we force the cat to go in,
Yeah.
but like we don't force the cat to actually bring it.
No, we just wanted to know if the cat is the one causing the
Affecting.
lamp
Exactly.
to fall on the ground or not. But since we don't have the full information if it is the earthquake, you need to find where earthquake is not happening, but you force the cat inside.
So like, you gave an example like using machine learning to predict why the customer is dissatisfied. In some situations, isn't it better to do a review or something like that because I think
Surveys.
So surveys, yes.
Yeah.
Because I think machine learning is a bit resource intensive. So in what type of situations do you recommend using machine learning, and in what type of situations do you recommend doing a survey or something?
Well, not everyone does surveys.
Yeah.
But here, like we're not trying to see. It's like trying to understand like what is the reason the customer, like decided not to buy from us anymore. We just wanted to see is the delivery rate specifically affecting the. Of course, you can do like is it because you can ask them is it because of the delivery time that you stopped buying from us. But like with this data, you can just basically calculate.
Yeah, so if I can add on that,
Yeah.
basically you can do both because when you're giving the survey and when you get that back, that's data that you can feed the machine so that it can learn it and then give you an answer based on what it saw from the survey. So you can do both.
Okay. Then, if you don't have questions, that means you understand everything. So we can do this now.
Do you know the code?
Yeah. So quickly join the count. You are still doing the live stream. Okay, so is everyone in?
Not yet. No.
Okay, I'm
PPC flashback.
Okay, I'm gonna count to 5. 1, 2, 3, 4, 5. Start. What does conditional probability represent? Okay, so yeah, the conditional probability is like trying to find the probability of y given that we know the value of x. So yeah, that x is observable. Okay. Let's see this. Okay, Anna first please, and then Shaz. What is the main difference between correlation and causation? Everyone understood this. Okay.
Anna is always littering.
Cheating?
Causation versus correlation. Which one is answer?
This would be a
What?
middle.
This is yeah, directed as
Did you guys? Okay, let's. Oh, we can't see the picture, right? Okay.
There
Anyways,
should be a way that
show media.
Click show media.
show me media.
Okay, so if we take a look, it's kind of complicated if you take a look at the things on top, but imagine you're not looking at this. Imagine you condition everything to not look at this, right? You see these two. The arrow is pointing directly to the final grade, which means this causes this. If it were pointing on both sides, so if these two didn't have an arrow, or if they had arrows that pointed like this, then that would be just correlation, but they didn't cause each other. But in this case, they are causational.
So if it is dark, basically it is
Yeah.
Okay. So because it's
pointing. Yeah, it has the
Yeah.
arrow and it's directed.
You didn't have to look at all the on
Yeah.
top, but
And I'm still on the Which statement is a fundamental rule of dark? So yeah, the first rule is directed. Arrows not correlation but causation. So like x causes y, that is directed, and cyclic as no variable can cause itself again. So it could not be in a cycle. Traditional machine learning models are mainly designed to answer which type of question?
No, no.
okay. So specifically for the blue one, because everyone else didn't think of the other ones, the blue ones, that would be causal machine learning. It's in the name, the cause, and therefore it would look at the directed acrylic graph, it would look at the causes, the different ways that we are going to have different results. So the what ifs, which is here and here, and then yeah, here is just observation, a little bit of a more general that's traditional.
Which one is a collider? This is graph. Which one is
Which one?
How did you get okay. So just to summarize, collider is when there is two arrows pointing toward a variable, and confounder is when there is two arrows coming out of it. So in this case, Z would be a confounder, not a collider. So why is that the right answer? which one of this is d-separated? This is the rule. I explained this twice.
Teacher, bro.
Only one person. I think I have to explain maybe again. Okay, so what did I say? What are the rules of d-separation? So the first one is if there is a collider between them, they are d-separated. So if there is a collider between them, they are d-separated. The second one is if we condition on a variable, they will be d-separated. So here, v is conditioned, so u and y will be d-separated. The reason this is a collider but this and this are not d-separated is because the third rule says if a collider is a condition, it will no longer act as a collider. So that's why t, even though it's a collider, it will no longer act as a collider. So u and x or r will remain connected. This one is co-founder, okay? This, everyone should get this one.
Why? So at least they keep us all have one mistake.
One person sticker. So I mean, yeah, I explained it earlier. So, yeah.
Explain again.
If two arrows are pointing toward the variable, it's a collider, and if two arrows are coming out of the variable, then it is confounder. So that's why Z would be the confounder. Okay. So our ninth question, what does the expression this represent?
You put it away.
No, he did yellow.
Okay, so
Yeah. Okay, so remember what I told you guys? If you've done coding, to do an intervention, you need to do a specific type of code, and that type of code is do. And when you do the do, you force the variable to do something else. It's, for example, the cat. We force the cat into the house. So that's what do does. I'm curious about the people who put observe. But okay, it's okay. No, we don't observe. That would just be observing P and the probability of P when Y. But if you do, then it's forcing something to happen.
yeah, so that's the main difference between traditional machine learning and causal machine learning.
Mm-hmm.
So we're actually intervening, not just observing.
Oh, maybe she knew answers. The ones.
Maybe she's paying attention.
Okay. What the fuck? Bro, he answered.
I did it. I already.
Bro, you have to be top 3 at least.
Why?
Why?
Everyone got it right.
Oh, everyone.
So, causal
Single
machine learning,
one.
coding, everyone. Third place. First place, of course.
Cheater.
First place. Anna.
So why you took out?
Thank you everyone for coming. Hope you enjoyed the
Thank you for amazing presentation.
Thank you.
You see? Yeah? Tables.
Oi, 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 congrats.
How did you like the dishes actually? No. Actually, you were like 8,000.
It's so easy, like we studied the statistics in
No, she told me in Darija. She told me in our language that she was teaching.
Hello, Adam. What do you think? Did you understand? Not a single thing.
That was just me being.
Yeah, you don't even need. No comen nada. Silly. Don't you have to do a lot of math? Really? It's a lot of chemistry. But chemistry is math.
Oh, no, I think you walk a lot of math, but I don't have that.
I think you're not going to be able to break through.
I know. Bro, actually, basketball.
Okay, that's a future new problem. But did you like the talk? Everyone had German, no one could come. I think you don't have the plus or something.
That's because a lot of people.
Like, my people.
She's a good student. So actually, play games.
It's a 3-hour German. Who would do that?
Next time, actually.
Anyways,
How was
it was cool. It was very chill. Like, it's perfect. I wasn't stressed or anything. Like, little. Listen, I'm gonna tell you something. I spent so much money on Littles. I spent a lot of money.
Bro, I still didn't care.
I can't get over you liking the actual potato though. How much like it?
No, it's not that bad.
What do you mean it's not that bad?
I liked it so much.
Yeah, that's, bro, you're so
I was trying to accompany you with the work, but no. ¿Te puedo tomar foto con Alfredo con su presentación? Okay.
around 17, 18 people.
bad.
It's a birthday, actually. Competition. Temperature.
No,
30 all separado.
30 plus people.
But what is it for dinner? No, I'm gonna have good dinner. Yeah, I don't wanna. Bye. Thank you for coming.
He's the richest guy.
This is going to be my story.
Gracias.
And it's more.
Y después con la ganadora.
But still, like, oh, Joe! I thought she was talking about the lecture.
Espera, acuérdense. Hey, dame tuyo. Dame el tuyo. If you don't like them, if you don't like them, I'll take it. Okay. Because the lighting is always bad here.
The Mongolian thing.
I feel like it looks nice. Your face is like, move more here because the numbers are in your face. No, more, sir. Yeah, like.
No, not really. I'm not really.
No, let's no, wait. Tell them to do it better here, because like
Okay, I think yeah, this
okay, yeah, because the screen actually looks better.
No other area kind of.
You're back.
It's very traditional things.
Ready? Okay, I like this. Yeah, that's the scale. Now you got the scale.
How is it?
We do it like with that. Wait, no, move. No, okay, good.
It's from Mongol.
Okay, now we're with the winner. Okay.
Oh, I get it depicted.
Anna was the winner.
Now with the winner. You have to clear. You guys show your middle. You'll be in the middle. Okay? Show your middle. Should I divide it?
You have to bite it.
Can I? Yeah.
One with this and one with that.
No, please. Ready? 1, 2.
Straight up.
Okay, now with that same like.
You don't have to actually.
Stop.
That's good for us, like, at this.
It's a good thing, you know.
This is really fun. Post this one, okay? Okay. Okay, thank you. No worries.
Inshallah, man, sometime soon.
We'll post it. Yeah. I'm never gonna come in Mr. Sexy. Be fine. Never win it again. Never win again. No, please.
Wait.
I do. I care.
Because I went like
No push. Es que tenía la
and they told me that we still do not tell them.
La persona me quedo parada.
They get them.
How's Ahmed doing?
He's not gonna tell me, you know, I fucked
Yo soy checkpoint.
I can answer you next time. I'll tell you inside. Soon he's fired, they're gonna know how he's
Monday, Friday, Saturday.
A mí no me interesa.
Harun really likes it.
Wiki.
Den Schein.
Oh, I hate this phrase. Ah, wiki.
Good morning, sunshine.
Says hello.
Got it. You don't have context. You need context. You need long friendship, you know, to understand.
Sorry, guys. You want to call Nazreen maybe? Actually, it's related to her.
Ahmed.
No, you were there.
And to breathe.
Yossi.
The live is over.
No, can you go to the QR code slide?
It's cringe. Wait, you know this one? No. I know it, but not like that.
Yeah.